Thank you. Thanks very much for the invitation. And this is joint work with Ilan, Kremer, and Eyal Winter. So in their famous article, Alken and themselves explain that incentivizing agents in teams can be challenging. They write that with team production, it is difficult solely by observing total output to either define or determine each individual's contribution. Each input owner will have more incentive to shirk when he works as part of a team than if his performance could be monitored easily. Now, monitoring agents' individual performance is costly, so there is the question of how monitoring should be optimally structured. They write that the cost of metering or ascertaining the marginal products of the team's members is what calls for new organizations and procedures. So in this paper, we study what is an optimal monitoring structure for a principal who wants to incentivize a team of agents to work. At one extreme, the principal may only be able to observe a performance signal for the overall set of agents. At the other extreme, the principal may be able to observe a performance signal for each individual agent. Our main interest is in understanding what happens in between these two extremes when the principal can verify more than just the overall performance of the team, but is constrained in her monitoring capacity. We want to understand what is an optimal monitoring structure in this case that minimizes the cost of incentivizing the agents. Now, the work that follow Alken and themselves challenged their view by showing that actually the monitoring structure does not matter under certain conditions. This is the case in the seminal work of Holmstrom on moral hazard in teams when we assume that agents are risk neutral, as we're going to assume in our model. And it's also the case in the work of Picard and Ray and McAfee and Macmillan, which feature not only moral hazard, but also adverse selection. These papers find that a principal can do equally well when she only observes the overall team's performance as when she observes each individual's contribution. Now, critically, these papers are only concerned with partial implementation, namely with inducing a team of agents to work as some equilibrium outcome, and they ignore the possibility that other equilibria may arise in which some or all of the agents choose to shirk because they expect that other agents will be shirking as well. And Mukherjee and Reichenstein make this observation when they discuss the work of McAfee and Macmillan, and based on this, they suggest that perhaps the value of monitoring is in avoiding such bad equilibrium outcomes. That is precisely the view that we are going to take in this paper. We are going to develop a theory of monitoring that is based on the need to address the strategic risk that agents in an organization face about the effort choices of other agents. We are going to show that for a principal who wants to uniquely induce a team of agents to work, monitoring will indeed be valuable, as proposed by Alken and themselves. And moreover, we are going to find that the design of monitoring then becomes a key tool for incentive provision, which has implications for organizations. So I mentioned already some of the related literature. Let me also say that the paper belongs to a growing literature on contracting with externalities, which was pioneered by Ilya Segal, and which for the most part also focuses on studying optimal unique implementation mechanisms as we do. Now, given the time constraint, let me move on now to the model. We have a very simple model. We want to focus on the question of monitoring. So the setting for incentive provision is going to be very stylized. There are M agents, and each agent I in the set M performs an individual task. Each agent is going to privately choose whether to shirk or work on his task. I'll denote this by 0 or 1. Shirking is costless, but working entails a cost of CI for agent I. So the heterogeneity in effort cost may be due to differences in agent skills or differences in the difficulty of the task that agents work on. Given his effort choice, the agent is going to complete his task with some probability. This probability is P1 if the agent chose to work, and P0 if the agent shirked, where P1 is greater than P0. The principal will monitor the agent's performance by assessing the completion of subsets of tasks. So formally, we are going to define a monitoring structure pi as a partition of the set M of agents. And I'm going to call the parts S in this partition pi the monitoring teams. So the idea is that the principal will partition the set of agents into a number of monitoring teams, And then for each monitoring team, she will be able to assess the joint performance of the agents in that monitoring team separately from the other agents. So she can isolate the performance of each monitoring team. We are going to focus on performance signals that are binary and supermodular, supermodularity reflecting the fact that agents' efforts are complementary in delivering a good performance signal. In particular, we are going to assume that for each monitoring team S in the monitoring partition pi, the principal can only verify whether or not all agents I in S have completed their task. So that means that given a profile of effort choices, a monitoring team S is going to deliver a good performance signal with a probability given by the product of the individual conditional task completion probabilities, and it's going to yield a bad signal otherwise. What is the cost of monitoring? We take a monitoring cost that takes the form of a capacity constraint. So the principal will be able to specify any monitoring structure pi, so long as the number of monitoring teams in pi, namely the number of parts in this partition, does not exceed the bound that we denote by m bar. So if m bar is equal to the number of agents m, this capacity constraint is non-binding. If m bar is equal to 1, that means that the design of monitoring is moot because the principal can only observe a performance signal for the whole set m of agents. For our baseline setting, we are going to impose no constraints on the principal's monitoring structure other than this capacity constraint. But of course, in applications, there may be additional constraints that may arise from the production function or other organizational arrangements. So these features in general are going to limit the principal's ability to group the agents in order to monitor their performance jointly. And so we are going to see later on that we can study the implications of such constraints as by studying them as constraints on the allocation of agents to monitoring teams. So the principal's problem is to choose a monitoring structure pi, which is going to deliver performance signals as I just described. And then for each monitoring team S in pi and each agent I in S, the principal will offer the agent a contract to induce him to work. We are going to focus on public contracts and assume that agents are protected by limited liability. So that means that without loss, the contract for an agent I in a monitoring team S is going to simply specify a bonus BI that the agent will receive if monitoring team S delivers good performance and no payment otherwise. I'm going to
sorry, I missed. There was no cost of a partition.
So as I said, the cost is a capacity constraint. So that's how we are modeling the monitoring cost. So you can specify a number of monitoring teams that does not exceed m bar. So this is going to be how we model the monitoring cost.
So one would think the optimal thing is just to do the maximum size if there is no further cost.
We are going to get there. So you just have to give me a few more slides.
Okay.
So the bonuses that the principal specifies for the agents in a monitoring team S, let me call that resulting bonus scheme BS. These bonuses are going to define a simultaneous game among the agents in S. In this simultaneous game, each agent is going to choose where to work or shirk. And an agent's payoff is going to be his expected bonus payment minus his effort cost if he chooses to work. So as I said, we assume that agents are risk neutral. The principal's goal is to uniquely induce the agents to work at the least possible cost. So in each of the simultaneous games that we are defining, we want there to be a unique Nash equilibrium. And in this unique Nash equilibrium, we want all the agents to be working. There is a technical issue, which is that the set of bonus schemes that uniquely induces agents to work is an open set. So formally, we define this by saying that a bonus scheme BS for each monitoring team S in pi uniquely implements work, UIW, if for each S in pi and every epsilon greater than 0, all agents I in S working is the unique Nash equilibrium of the game that is defined by this bonus scheme when I augment the bonuses by epsilon. Okay? Pradeep, you're still unmuted. So let me define f of S as the probability that a monitoring team S yields good performance conditional on all agents in S choosing to work. So it's given by this expression. I can now write the principal's problem as we have here. The principal is going to choose a monitoring structure pi that satisfies the capacity constraint that the number of monitoring teams does not exceed m bar. And then she's going to choose the bonus scheme BS for each monitoring team S in pi in order to minimize her expected incentive cost subject to the unique implementation constraint. The expected incentive cost is straightforward. I'm adding over the monitoring teams and then the agents in each monitoring team, and the cost of incentivizing the agents. The agent is simply the bonus that I have to pay when the agent's monitoring team yields good performance. Okay. Let me mention that we are studying unique implementation in Nash equilibria, but in our setting, this is equivalent to studying unique implementation in rationalizable strategies. And the reason is that given our assumptions, the game that we are inducing in each monitoring team is a supermodular game, so we can apply the results of Milgram and Roberts. So this is the problem that we are interested in solving. And before we do that, and partly to answer to Pradeep's question as well, we want to study as a benchmark what happens if we ignore the unique implementation constraint. So I'm going to consider a relaxed problem where I'm ignoring this constraint. And so I'm going to study what happens under partial implementation. Under partial implementation, the principal simply wants to induce the agents to work as some equilibrium outcome, not necessarily the unique one. So that means that given a monitoring structure pi, for each monitoring team S in pi and each agent I in S, we want to offer the agent a bonus so that the agent prefers to work rather than shirk when he conjectures that every other agent in monitoring team S is going to be working. Okay. So that's the incentive constraint that I've written here. And of course, the principal will satisfy this constraint with equality. So that gives me this bonus that we are going to offer to any such agent I to induce him to work. All I need to do now, yes.
Marina, just a quick question on the setting. It looks like that you have symmetry in the effort probabilities, but possibly asymmetry in the cost of choosing efforts. Is that right?
Yes. Sorry, do you still see my screen?
Yes.
Sorry, it's just, okay, something happened in my computer.
No, you just made it a little bit smaller.
Yeah, so just 1 second. Where is this? Oh gosh, sorry, something is not. Okay, let's try one more time. Yes, but I can answer your question in the meantime, I think. So you're saying that I have, there we go. So now you can see it's full size, right? So yeah, so we have heterogeneity in the effort cost. We have the probabilities of task completion. There is no heterogeneity there. We studied that at the end as an extension. So let me try to make some time for that. But things are super clean here, and there is I can try to explain what changed in that case. But you know, the general logic is the same, but there is one additional complication in that case. We cite that as an extension. Yes. Great. So now all I have to do is substitute with these bonuses into the principal's objective. And so the principal's problem, remember, we are in this partial implementation benchmark, reduces to choosing a monitoring structure that minimizes her incentive cost, which is now given by this expression. Now, there is nothing in this expression that depends on the monitoring structure. And so what we obtain here is that under partial implementation, the principal's cost of incentives is independent of her monitoring capacity and her monitoring structure. Of course, here we are obtaining this result under the assumptions that we have made. But we view it as a meaningful benchmark precisely because it coincides with the results of this prior literature that I have mentioned, which shows that this result holds under general conditions. So we obtain that under partial implementation, the principal does not care about whether she can only observe the overall performance of all the agents, just one signal for everyone, or whether she can verify each agent's task completion. And so going back to Pradeep's question, if we only care about inducing the agents to work as some equilibrium outcome, then we don't necessarily will be exhausting the principal's monitoring capacity. Okay. How we view this is that, well, partial implementation, as we know, suffers from the standard criticism, which is that we don't know how we get to choose the equilibrium that agents are going to play. But moreover, here it also suffers from the fact that it cannot capture the benefits of using finer monitoring structures. And so now that we have this benchmark, we are going to move on to studying our unique implementation problem. And it is in this sense that the theory of monitoring that we'll propose is going to be one based on the need to address agents' strategic risk. All right, so to solve our problem, we proceed in 3 steps. First, we take any given monitoring structure pi, and we characterize optimal incentives for any such monitoring structure. Second, we use the characterization of optimal incentives to solve for an optimal monitoring structure. And finally, we study the implications, as I mentioned before, of introducing additional monitoring constraints. So given that we have little time, let me just state the result for the characterization of optimal incentives. Here we are fixing any given monitoring structure pi, and we want to understand what are the optimal bonus schemes that the principal will offer given pi. And it's clear that given pi fixed, the principal is solving for an optimal incentive scheme for each monitoring team in pi separately. So what we obtain is that if B star is an optimal bonus scheme for monitoring team S in pi, then it has to be that there is a permutation of the agents in S that orders the agents by increasing cost of effort, such that for agent in position J in this permutation in monitoring team S, the bonus that we are going to offer to the agent is given by this expression here. So what we see is that we obtain this very nice simple expression for the bonus that we offer to the agent. It's simply equal to the Nash bonus that we derive in the partial implementation benchmark times a compensation factor that I'm going to call RSJ for this agent in position J in the permutation for monitoring team S. So this compensation factor is telling us that in the case of unique implementation, we need to offer higher bonuses to the agents compared to the case of partial implementation. Naturally, we need to compensate the agents for the strategic risk that they face about the effort choices of other agents in their monitoring team. This strategic risk arises because for each monitoring team, the principal can only assess the joint performance of the agents in that monitoring team. So the possibility that another agent in my monitoring team may be shirking is going to lower the marginal benefit of my effort, namely the marginal effect of my effort on delivering a good performance signal. That's going to lower my incentive to work and hence imply that I require a higher bonus to be willing to work. So these bonuses are such that the first agent in the permutation will be indifferent between working and shirking, conditional on everyone else shirking. The second agent will be indifferent, conditional on the first one working and everyone else shirking, and so on and so on. Naturally, agents who are placed later in the permutation for a given monitoring team S are provided greater assurance that other agents in the monitoring team will be working, so they require a lower compensation for strategic risk. And so this also explains why an optimal permutation places higher cost agents later in the permutation compared to lower cost agents. Facing strategic risk about other agents' effort choices is more costly to an agent when his own effort cost is higher. And so as a result of this optimal permutation, we obtain also that agents whose effort cost is lower in a monitoring team S and hence are placed earlier in the permutation will also receive higher rents compared to those whose effort cost is higher. Now, our main goal here is to use this characterization of optimal incentives to derive an optimal monitoring structure. So the same way as I did in the partial implementation benchmark, what I'm going to do next is take these optimal bonuses and substitute them into the principal's objective. When I do that, I simplify the principal's problem. I reduce that problem to choosing a monitoring structure pi that minimizes her cost of incentives, which is now given by this expression here. And what we find now is that the principal's incentive cost does depend on the monitoring structure, and it does so via these compensation factors that we are calling RSJ. Right? If these compensation factors were all equal to 1, we would be back to the partial implementation benchmark where the monitoring structure does not matter. And so it is just the basic properties of these compensation factors what is going to allow us now to derive the optimal monitoring structure. Let me highlight here these compensation factors are greater than 1, and they are strictly increasing and convex in the size of the monitoring teams. So because they're increasing in the size of the monitoring teams, we obtain that the principal benefits from minimizing the size of the monitoring teams. And so the first result, going back to Pradeep's observation before, is that if the principal chooses a monitoring structure pi star, if this is optimal, then it must be that pi star exhausts the principal's monitoring capacity. And so indeed, we want to specify a number of monitoring teams which coincides with the monitoring capacity M bar. The intuition is straightforward. If we are not exhausting the monitoring capacity, I can always take a monitoring team, split it into two, and I will be reducing the agent strategic risk and hence the principal's incentive cost. So once we set up the model, solve for optimal incentives, and substitute into the principal's objective, this result follows in a straightforward manner. But we view it as an important result precisely because it is in stark contrast with the case of partial implementation, and it supports the view of Eyal and themselves that monitoring does matter. Now we have established that we want to specify M-bar monitoring teams. Now we need to solve for what is an optimal allocation of agents into these M-bar monitoring teams. Our main broad result is that the principal benefits from specifying monitoring teams that are homogeneous with respect to each other. So we are going to first show this with respect to size. We show that the principal wants to specify monitoring teams of equal size, of course, up to integer constraints. And so if pi star is an optimal monitoring structure and S and S prime are in pi star, then their size cannot be different by more than one. And absent integer constraints, all monitoring teams are of equal size. So here is a sketch of the proof. Suppose that S is larger than S prime by more than one. We show that we can improve the principal's objective by moving an agent from S to S prime. Let me take a lowest cost agent in monitoring team S. This is an agent who would be placed first in an optimal permutation for monitoring team S. It suffices to show that I can lower the principal's incentive cost, let me call this agent I, by moving this agent I from S to S prime and also placing him first in the permutation for this perturbed monitoring team S prime. The advantage of doing it this way is that as I move agent I from S to S prime, I'm not going to affect the strategic risk that any other agent faces because I'm always making it dominant for agent I to work. And so I'm not affecting the cost of incentivizing the other agents. That means that all we need to show is that we are lowering the strategic risk that agent I faces, and that indeed follows because we have assumed that monitoring team S prime is smaller than monitoring team S by more than one. So agent I will face lower strategic risk when he's moved to monitoring team S prime. So this is telling us that the principal benefits from dividing the organization into equally sized sections, with each section having its performance evaluated separately. If all agents were identical, then I would be done because equally sized monitoring teams would imply identical monitoring teams. The next question then is what happens if agents are heterogeneous, and in this baseline setting, we are allowing, as Dirk said, for heterogeneity in the effort cost. So here again, we find that the principal benefits from specifying monitoring teams that are homogeneous with respect to each other. What that means is that the principal wants to specify monitoring teams that are heterogeneous within. So let me be more precise about that. I'm going to define an anti-assortative monitoring structure. Let me take a permutation phi of the whole set M of agents that orders the agents by increasing cost of effort. I'm going to call the first M-bar agents in this permutation rank 1, the next M-bar agents rank 2, and so on and so on. I'm going to say that a monitoring structure pi is anti-assortative if no monitoring team S in pi has two agents of the same rank. For some such permutation phi, we could have multiple ones if some agents have the same cost of effort. Okay. So let me illustrate with a very simple example. Suppose that we have only 4 agents with effort cost given by C1 less than C2 less than C3 less than C4. And suppose that M bar is equal to 2. So we know we are going to specify 2 monitoring teams. Right? I'm going to call the 2 lowest cost agents rank 1, the other 2 are rank 2. So here is how we can construct an anti-assortative monitoring structure. We take the rank 1 agents and we assign them to different monitoring teams. For example, agent 1 to monitoring team S1, agent 2 to monitoring team S2. Then I go to the next rank and I want to assign the agents in rank 2 to different monitoring teams. For example, agent 3 to monitoring team S1 and agent 4 to monitoring team S2. And I could keep going if I had more agents. At the end of the day, I have an anti-assortative monitoring structure because no monitoring team contains 2 agents of the same rank. Why is this interesting? Well, because we obtained this result, we find that there exists an optimal monitoring structure that is anti-assortative. And moreover, absent integer constraints, every optimal monitoring structure is anti-assortative, and every anti-assortative monitoring structure is optimal. So the idea is the following. Suppose that pi is an optimal monitoring structure and it's not anti-assortative. Then there must be two monitoring teams in pi, S and S prime, and an agent in S and an agent in S prime, such that the agent in S has a higher cost of effort than the agent in S prime, yet he's placed earlier in the permutation for S than the agent in S prime is. So then we can swap these two agents, and by doing so, we are going to be weakly lowering the principal's incentive cost. And moreover, if we perform this swap for every other pair of agents with these properties, we are going to construct an anti-assortative monitoring structure. Absent integer constraints, any such swap would strictly reduce the principal's incentive cost, and that's what delivers the uniqueness results. The intuition is simple, and it's related to the things we discussed before. It's about the optimal provision of assurance across agents. Remember, we said that facing strategic risk about other agents' effort choices is more costly to an agent when his own effort cost is higher. So the principal wants to provide greater assurance to higher cost agents relative to lower cost agents about the effort choices of other agents. So that's the logic that, given a monitoring team S, allow us to establish what an optimal permutation of the agents in S was. We said we want to place higher cost agents later in the permutation. Well, an anti-assortative monitoring structure is optimal because it allows us to provide assurance efficiently across agents, not only within a monitoring team, but across monitoring teams. So the key defining feature of an anti-assortative monitoring structure is that no agent is going to face higher strategic risk than another agent whose effort cost is comparatively lower, no matter to which monitoring teams these two agents belong. And so in terms of the implications of this result, of course, there are implications for the structure of monitoring. Again, we find that we want to divide the organization into equally sized sections, but moreover, we want each section to contain agents from every rank. And so this is the sense in which sections will be diverse within, but similar to each other. And there are also implications for pay, because once we have an anti-assortative monitoring structure, we obtain that compensation factors are determined by agents' effort cost. And so we find that lower cost agents, namely higher skill agents, are going to receive higher rents than lower skill agents, not only within each monitoring team, but across the organization.
Just wrap up in like 2 minutes.
2 minutes, perfect. So that's our baseline setting. And the nice thing is that we can provide a general characterization of an optimal monitoring structure. What is less satisfying is that we are giving the principal a lot of flexibility for how to monitor the agent's performance. And in reality, there are constraints that are going to limit the principal's ability to group agents in an arbitrary manner in order to monitor their performance jointly. So what we do in the second part of the paper is we introduce these constraints. We look at the constraint problem where we take the agents to be ordered exogenously along the line, and we restrict attention to monitoring partitions that divide this line into consecutive segments. And so that exogenous order would represent the production process, which is given, and which is going to limit the principal's monitoring structure. And so formally, we define a constraint set of partitions of the set M such that now the monitoring partition pi not only must have a number of parts no greater than M bar, but moreover, for each monitoring team S in pi and agents I less than J less than K, we require that if I and K belong to a monitoring team S, then agent J also belongs to monitoring team S. Let me jump to the result of what happens here. Of course, there are some of our results that are going to extend to this constraint problem, namely the fact that the principal wants to exhaust her monitoring capacity is going to remain true. And if agents are identical, these constraints will have no bite. But when agents are heterogeneous, of course, now an optimal monitoring structure will depend on how agents' effort costs vary along this exogenous order. So the main result here is that when the agent is constrained in the composition of the monitoring teams that she can specify, as it is the case here, then she's going to adjust the size of the monitoring teams. And so to provide greater assurance to higher cost agents, what she's going to do is place higher cost agents in smaller monitoring teams compared to lower cost agents. We are studying here a problem where the principal is designing both transfers and monitoring. And so we obtain results for how these two different tools are used differently across agents. What this constraint problem delivers is a result that says that the principal will incentivize high-cost agents, namely low-skill agents, to work by using by monitoring them closely and offering them lower rents, compared to the higher skill agents who are going to be monitored, who are going to be incentivized, with less monitoring and with higher rents. But I'm running out of time. So Derek, I think I'll chat with you about that extension later on. So as I said, we study what happens when there is heterogeneity in the task completion probabilities. We also discuss the fact that we have only look at monitoring structures that take the form of a partition. So we have some discussion, but I think more could be done. And we also talk about the performance signals that we have assumed in our model and the fact that they would be optimal in an augmented problem where the principal can choose the performance signals under some constraints. But I think I'm done, so probably I should stop here. I'm out of time. Thank you very much.